So we will be talking about neural networks today. Last week, as you remember, we started with genetic algorithms for the artificial intelligence part of our class. And this week we will be discussing neural networks. Today it's gonna be a little bit theoretical, but we will have two concrete examples at the end of the lecture, where we will be creating our neural networks with TensorFlow. But we will try to understand the definitions, the concepts, how the neural network works, how a neuron actually works. And then in the incoming weeks, we will be working on more advanced stuff. Okay, so as usual, we will be starting with the summary of the last week. Then we will be seeing what are neural networks, what is a neuron, and what's perceptron. We will be talking about the building blocks of neural networks, and then we will see how we can apply neural networks to some problems. Then we will see how we can train neural networks, and then we will be seeing how we can write code on neural networks. And it's gonna be pretty interesting. This week's lecture, we will be seeing Google Colab, and we will see how we can work with Google Colab. So stay tuned, try to follow the lecture. Okay, let's start with the summary of the previous week. So we have seen the steps of genetic algorithms, and then we have seen the details of each step, and then we saw the definition of genetic algorithms, and then we have seen the limitations, where it works in a good way, where it doesn't work. So we saw that it's actually used for optimization problems. We worked on an AppSec problem as well as traveling salesman problem, if you remember. And now we have seen it doesn't always find the best solution, but it finds the better solution, or it finds a solution which is good enough. That was the thing with the genetic algorithms. And it's basically a methodistic inspired by the process of natural selection. We have seen that it's not the strongest of the species that survive, nor the most intelligent, but the one most responsive to change. And that's usually the concept somehow misunderstood by people. People always think it's the strongest of the species. That's not true. Basically, it's the one who is most responsive to change. And being the fittest makes you, gives you the opportunity to have a lot of children. And we have seen the concept of mutation, crossover, and selection for the species. Okay. And we basically saw the steps of the genetic algorithms. We first start with an initialization, then we need to have a fitness function for decisions. And then with our initial population, we make a selection. Then when we create new generations with crossover and mutation, these two operators were used to create new generations. And then we carry some good performing part of the population with the selection to the next generation. And we follow this iteration until its convergence, or we follow it until its stopping criteria. And we have seen these examples. The idea was we start from here and we would like to go to this cell, and every movement our bot or the robot makes was called a gene, and the combination of these genes were called the DNA. Okay, if you remember. And the fitness function was measuring how good the robot was performing. For example, if the robot stays here, it started here, it followed this direction, right, down, left. Okay. If it's followed this, then the fitness function says, okay, it's far away from the final point, and the distance is this distance. Okay, that was the fitness function. We needed this fitness function in order to understand how good that individual DNA is performing. And then we have seen a concept called population, and the population was basically the combination of these DNAs. And once we create a population, we were sorting this population with respect to their fitness, and then we were choosing the best performing elements, and that was called the selection. And we have seen there is actually no best way to select the best from the population. Okay, in one of our examples we selected half of the population, but in another example we just selected 3 or 5 of the best performing elements. So there is no such a thing that we are selecting the best, for example, half or 1/3. That totally depends on the problem you are trying to solve. Now, once we select some part of the current population, we are using the operator crossover in order to create new individuals, new DNAs. And the idea behind the crossover was you were taking some DNAs from the mother and some DNAs from the father, and we were coming up with a totally different offspring. And we had another operator called mutation, which was randomly changing the DNA. Okay, this is totally random. And we are not changing all the DNAs. We're just randomly finding a DNA, selecting, for example, let's say we say we're going to change this DNA with mutation, and we're just changing it from this direction to this direction, for example. And these operations were creating new DNA, and by combining these DNAs plus the DNAs created with these two operators, we were having another generation, and we were following this loop until its convergence. And we solve a problem called the knapsack problem. The idea was we were going to go to camping, for example, and we have a bag that can carry just 30 kilograms, as you see here. And the problem is we have a lot of items with their survival points, and we would like to choose the best items that's good for our survival. And we have seen if we try to solve this problem in a brute force way, at some point when we exceed, for example, the item number 25, we saw that basically the time consumption is too much for our computers. So we need to somehow solve this problem more intelligently, and the genetic algorithms is quite good for this kind of problems. So the initialization phase, that's creating the gene pool or the population in a totally random fashion. Okay, there is basically no rule to create the initial population. You just start randomly, and then you select a fitness function. For the knapsack problem, for example, the fitness function was the survival point. For example, if you carry a rope, its weight is 3, and its survival point, its fitness function is 7. Okay, so you would like to maximize this part as well as this part. So basically you would like to maximize this part, and this part, this column, the weight part, is the constraint. Okay, this is a constraint optimization problem. So you need to maximize the survival points, but you have constraints. You can just carry 30 kilograms, no more than that. So you cannot carry this one and this one together. Okay, and then we were applying a selection. We saw two kinds of selection with one fixed point or two fixed points. In this kind of selection, you basically select mother and father in different loops. With this kind of two fixed point selection, you select both father and mother together. And then we apply the crossover. There were different strategies with crossover. For example, you could select from this half of the first parent and this half of the second parent. That's one strategy. That was called one-point crossover. And we have another strategy called multi-point crossover as well. So you select this part from this parent, this part from this parent, and this part from this parent, and you come up with an offspring. Basically, you can follow a different strategy to come up with another offspring like this one. And then we were randomly changing some genes. In this case, we changed this gene from 1 to 0, and that was the mutation part. Okay. And then we have seen another example that we debugged with PyCharm, basically that was a traveling salesman problem. I hope you were able to run it by yourself and debug it by yourself. There we have seen a function called mix, which was basically doing the crossover here, the crossover part, and the mutation part here. And we had seen two random partial mutations. One was randomly switching genes, and the other mutation type was inserting a gene to the sequence and removing the inserted gene from the sequence. Okay, we had seen two different mutation strategies. So revisiting the last week's quiz, the method we can use to resample data with sampling with replacement is bootstrapping. Initial population in genetic algorithm is constructed totally randomly. That's true. Which of the following operator genetic algorithms rely on? All of them, basically. So a lot of you guys couldn't answer this correctly. Please be careful. Which of the following is true for genetic algorithms? Strongest of the species survives. That's false. The most intelligent of the species survives. That's false as well. The one that's most responsive to change survives. Please try to remember that. Boosting trains its classifiers in parallel. That's false. That was basically the idea behind boosting. Changing the DNA randomly is called mutation. Okay, the seventh question was done correctly by very few people. By crossing over these two genes, which DNA we cannot get. Okay, 1, 1, 1, 1. If you get this 1, 1 and this 1, 1, you can get this one, right? 1, 1, 0, 0. If you take this 1, 1, and if you take this 0, 0, you can get this as well. So 1, 0. You see, there is no 1, 0 here. So you cannot have a crossover something like this. Okay, 0, 0, 0, 1. You can get the 0, 1 here. You can get the 0, 0 here. Okay, 0, 0 from here and 0, 1 from here. Which of the following is an application of genetic algorithms? Basically, all of them are application of genetic algorithms. You can basically create music with genetic algorithms. A tree stump is a weak learner with two levels. That's true. Genetic algorithms always find the best solution. Please be careful with this question as well. That's false. Genetic algorithms tries to find a solution that is not guaranteed to be the best. Okay, by summarizing the last week's content, let's start with this week's content. So basically, we have this concept of artificial intelligence. It's any technique that enables computers to mimic human behavior. Then we have machine learning. We said these are the mathematical tools we use for artificial intelligence. And now, with this week's lecture, we will be starting the concept of deep learning. Okay, and the definition for deep learning is extracting patterns from the data using neural networks. So this is a subfield of artificial intelligence, definitely. But the whole idea behind deep learning is we extract patterns from the data. Okay. So what does it mean extracting information from data, or why do we actually use deep learning now? Let's say we would like to make object recognition and we would like to recognize giraffes. Okay. If we don't use deep learning, we need to somehow define how we will be recognizing these giraffes. So one way, if you know a little bit about image processing, is you make edge detection and then you create the skeleton of the giraffe, and then by comparing the skeletons, you may be able to say whether this shape is a giraffe shape or not. Okay, so this is called handcrafted feature, because before we start the problem, the programmer said, okay, I'm gonna detect the edges, I'm going to create the skeletons from these edges, and then I will be comparing these edges in order to decide whether this shape is a giraffe or not. So there are two major problems with this technique. The first one is, since these features are handcrafted, meaning the programmer said we will be using the skeleton, we could be using another feature. For example, we could be using, I don't know, the shift features here or the hook features somewhere, but we decided to use the skeleton of the shape. Now let's see, if we didn't see this part of the giraffe, assume that we just saw this part of the giraffe. This is still a giraffe, right? But since we are basically comparing two skeletons of giraffes, if we don't see the head of the giraffe, it's highly likely that we will not be able to recognize this by handcrafted features. So this is basically the first problem. You need to see usually the whole object if you have handcrafted objects. And you can never be sure your handcrafted object will be giving a good result. Instead of doing that, we could be just using neural networks in order to find the best performing features. And that's the idea behind deep learning. So hand-engineered features are time-consuming, brittle, and not scalable in practice. So the idea behind neural networks is try to find the features by using the neural networks. Don't give any clue to the network. Just feed the network with data, and the network will decide which feature is the best for your problem. Assume that we will be doing face recognition, okay? And then we created a neural network. And somehow, by feeding a lot of face images to this network, our network creates first some low-level features, and then it combines these low-level features to mid-level features, and then it combines these mid-level features to high-level features. But in the process, you have basically nothing to say to the neural network. From start to end, basically the neural network decides which features will be used. Okay, that's why these features are not hand-engineered features. That's why these features can perform much better, because the neural network sees a lot of data, and by using this data, the network basically can decide which features are best for this problem. So, conventional machine learning approach, we have handcrafted features, for example, histogram of gradients. We get some samples, we basically extract these handcrafted features. So beforehand, we basically decided, the programmer decided, hook features will be used, okay? And then we extract hook features from these images, and then we apply a classification algorithm such as support vector machines, and then we get the results. This is the conventional classical methods for artificial intelligence or image recognition or classification, okay? With the deep learning approach, the operator doesn't have anything to say to the convolutional neural network or the neural network. Just forget about the convolutional part here. So there are two main roles for the operator. The first one is creating the network. So we need to create a neural network, first of all. And then we need to train that neural network. So that's basically what the operator does. Two things. Create the network and train the network. So here, the operator had to decide which feature was going to be used, but here the operator has nothing to say for the feature to be selected. It's the networks, the neural network's role to find the best performing feature for our problem. Okay, that's the basic difference between the conventional or classical machine learning approach and the deep learning approach. In deep learning approach, you create a network, you feed the network with data, and then you get the results. In between, you don't do anything. Okay, that's basically saying the same thing. We have inputs. If you are using classical machine learning techniques, you need an operator that needs to say we will be using these features for this problem, and then we apply a classification algorithm, and then we obtain an output. Okay, this is the classical machine learning cycle. But in deep learning, you have data, you somehow created a neural network. This is the neural network. And you feed your data to neural network, and then it decides, it extracts the feature plus the classification by itself. Okay. In this case, the classification is done automatically, but the feature extraction is done by the help of an operator, or the operator decides which feature will be selected. Okay. This is the basic difference between classical machine learning and deep learning. Okay, so if deep learning is so good, why we didn't use neural networks beforehand, people may ask. But frankly, people tried to use neural networks, for example, back in 50s. If you look at this picture, the history of stochastic gradient descent goes back to 50s. And the concept of perceptron basically goes back to 50s as well. But the problem was, there were three major problems using the neural networks. First of all, you need a lot of data for the neural networks, and in that ages, in 50s, 60s, you didn't have a lot of data, and you didn't have enough storage basically for this kind of data. Okay, but now we have larger databases, and data collection is much more easier. Data storage is much more easier. Okay. The second thing which you cannot underestimate is the hardware. Now we have GPUs, graphical processing units. Therefore, we can massively parallelize things. But in 50s, you just have computers that are weaker than our calculators nowadays. Okay, so basically, they didn't have the hardware resources to run the neural networks, and you basically need some software in order to create your neural networks. Now we have a lot of libraries. We will be using TensorFlow. PyTorch is also very popular for this kind of stuff, but we will be following TensorFlow. They are more or less same. The idea is you create a network, you train it, and that loop is quite similar with all the libraries. So there is not so much difference. So why couldn't we get deep learning up until now, and why we should use deep learning now? So this graph basically summarizes everything. If you have labeled data, and if you have enough computing power, if you have these two guys, then the basic difference between classical algorithms and deep learning is this. As you increase the amount of your data, deep learning performs better and better. Okay, the performance of deep learning algorithm increases if you can feed the deep learning algorithm with data. But with classical machine learning techniques, that approach is to apply to pretty quickly. So the performance doesn't increase too much. But if you have a lot of data with deep learning, you can get better and better results. So that's basically the difference. So neural networks are taking over, as you have seen with ChatGPT or Midjourney. They are basically doing a lot of stuff much better than human beings. But let's see what people did with neural networks. In speech recognition, Microsoft AI beats human. That's a little bit old news, basically, but that's something that happened. In translation, if you remember old ages, the automatic translation, especially for languages such as Turkish, was quite crappy. Right now, the translations are unbelievably good. That's because of the neural networks as well. We are using the neural networks in image processing quite a lot. So you can basically recognize or classify images with neural networks. We will be doing that in the following lectures. We will both classify and recognize stuff with neural networks. We will create images with neural networks. Basically, this example is recognizing and localizing objects by using neural networks. And this is the same problem with a different application area. With neural networks, people created artificial intelligence that can beat humans in AlphaGo, which is a pretty complicated game. With help of neural networks, we can now summarize the content of images. Okay, so these are basically generated by AI that's describing the content of the image. A man in black shirt is playing guitar, for example, or a construction worker in orange safety vest is working on road. That's pretty amazing, basically. And you can generate images. And this is all these faces are fake. They don't even exist. And you can do the same with, for example, Midjourney or Deepfake. We will try to make an image generation example in the following lectures as well. So humans can learn, solve problems, recognize patterns, create. And Marvin Minsky said, if the brain was simple enough to be understood, we would be too simple to understand it. So it really took a lot of time to understand the concept of neural networks. We will see why it did take this much time. But now it's in an amazing state. And if you make investment on neural networks, trust me, that's gonna pay. So in mid-80s, people said the brain is a mess of interconnected neurons, and people understood this in mid-80s. So what are these neurons and what does this perceptron means, basically? So this is a neuron, okay? You should remember this from high school biology classes. This is basically the neuron itself. That's the body of the neuron. That's called soma. All these little things are called dendrites, and this thing is called axon. Okay. So we have three parts. We have the central mass, it's the soma. We have these little things called dendrites, and we have this thing called axon. And the signals come from the dendrites to the soma, and things happen in soma, and a signal goes out from the axon. So this is basically how a neuron works in biology. And this is how a neuron works in mathematics. Basically, this is the soma. You can remember it from the sum. Okay. These are the dendrites where the input comes, and this is the axon where the output goes. And we have these things called weights. Okay. Each input is multiplied with a weight before it comes to the soma or the centroid. And in centroid, what we basically do is we multiply the input times the weight, and then we apply an operation here. And this whole operation is basically this. You get the sum of this input times weights, and you subtract this thresholds. And then if that's equal to 0 or bigger than 0, your axon fires a 1, otherwise it fires a 0. This is the simplest neuron you can get, okay? We will be seeing some different neurons, but this is like the most simple neuron you can get. And everything started with this neuron, okay? So we have the output of either 1 or 0, okay? And that totally depends on this equation. If basically the x1 times w1 plus all these things minus t is greater than or equal to 0, then we have 1 here, otherwise we have 0 here. Okay, so once people understood this concept of neuron in 50s, then they realized they can basically solve some logic problems, such as AND. So this is an AND operation, this is an OR operation, and this is an inverse operation. Okay. So how does it work? This is the simplest. You have the inputs the weight is -1. So input times -1 minus 0 is basically the NOT of that thing, right? Okay, so if you have 0 here, 0 multiplied by -1, that's 0, okay? And 0 minus 0 is basically 0. And if it's, since it is greater than or equal to 0, that's gonna basically be 1. So we started with a 0, we come up with a 1. So this is a NOT operation. And see, this is an AND operation. If x is 1, as here, and y is 1, it's 1 times 1 plus 1 times 1 minus 2. That's the threshold. That's the threshold in SOMA. And that's equal to 0. And remember this equation, if it is greater than or equal to 0, then this fires as a 1. Okay? And this was an AND operation. 1 and 1 is another 1. Okay? And if you remember from your logic or mathematics classes, a 1 and a 0 is a 0. Let's see whether this gate can solve this. So x is 1, y is 0. That's -1. And from our equation, it's smaller than 0. That means that's gonna fire 0. So this is an AND gate. And this is an OR gate. You can basically try it yourself. But the thing is, it cannot basically operate on all logic operations. So this is an XOR operation. Let's remember what XOR was. So if you have 0, 0, the output is 0. If you have 1, 1, the output is 0 as well. If you have 0, 1 or 1, 0, the output is 1. Okay, this is basically the XOR operation. And at 60s, late 60s, people realized that this neuron, the single neuron, cannot solve this problem. And that's because this neuron can just solve linearly separable problems. So this is an OR problem. Okay, and if you use this line that basically splits your space into two, which means you can basically use one single neuron in order to solve this OR problem. But this is an XOR problem, and there is no single line that can split the space into two. This is not linearly separable, so you cannot just use one single neuron. Once people realized this, they said, okay, this thing is not gonna work, basically. Then they realized they can stack these neurons together, okay? And they realized a single neuron is not enough to solve complex problem. But then they came up with something called multi-layer perceptron. It's not a neuron, but it's called a perceptron, multi-layer perceptron. And they realized they can basically solve the XOR problem, actually. And let's see how we can solve that problem. So when our input is 0, 0, we need to obtain a 0 here. Okay, try to follow this. This is not complicated, but that may be a little bit tricky. We have 0, 0 here. Okay, we have these weights. These yellow labeled things are weights, and these are the thresholds for our neurons. If we have 0 here, 0 multiplied by 1 is 0, 0 multiplied by -1, that's 0 as well. So we have incoming 0 here from this input. 0 multiplied by 1, that's 0, and that's 0 coming from this input as well. So we are here. It's gonna be 0 plus 0 minus 1. And since that's -1, it's gonna fire a 0. 0 multiplied by 1 is 0, and here comes a 0. Okay. And that's similar here. It's 0 times 0 plus 0 minus -1. Okay. So that's gonna be a 1 here, I think that's not correct for our initial problem. Just a second. So that's gonna be a 1, and that's sorry. So this is going to solve this 1 0 problem, okay? Because we will have a 1 here, we will have another 1 here. That's an AND gate. 1 plus 1 is 1. But here we will be having a 1. This is not correct. This is supposed to be a 1. But since this is an AND gate, 0 1 is going to produce a 0. Okay. So for 0 0 we will be having a 0. So this guy is supposed to be a 1. Let me change this. So when we have 1 0, as you see here, we should obtain a 1. Okay. So if you follow this with the same manner, we will have a 1 in this gate, we will have a 1 in this gate. 1 plus 1 minus 2 is going to be a 0. And if you remember this equation, it's greater than or equal to 0, then that's going to fire a 1. Okay, let's try to follow this. 1 times 1 is 1. 1 times minus 1 is minus 1. 0 times 1 is 0. 0 times minus 1 is 0. So 1 plus 0 is 1. Minus 1 is 0. Since this is a 0, it's gonna fire a 1 here. And 1 times 1 is 1. This part is going to be a 1 as well. And it's same here. Minus 1 plus 0 is minus 1. And minus 1 minus minus 1, it's gonna be a 0. Therefore, that's gonna fire a 1. 1 times 1 is 1. And since this is an AND gate, 1 plus 1 is 2. 2 minus 2 is 0. Since this is a 0, it's gonna fire a 1. Okay, so we could be able to solve the XOR problem with this multi-layer perceptron. We basically used this gate, which is an OR gate, and this gate, which is a NAND gate. Okay, and then by combining these two gates, we could be able to combining these three gates. This is an AND gate as well. By combining these three gates, we could be able to solve the XOR problem. So, do we actually need to always fire a 0 or a 1? We don't actually need to do that. We can have real value inputs. So our inputs, this x's, can be real values. The weights are, they can be real values as well. And at the outputs, we don't need to have a 0 or a 1. We can have a real value as well. And we will be using our good old friend sigmoid function in order to achieve this. So instead of using a simple threshold, we will be using the sigmoid function at the end of our network. So basically we have our inputs, weights, these are real values. We have n inputs, we have n weights. Now comes something like this. This is the bias, if you remember from our regression classes. This is another input as well. But this is a special input. You don't feed it from outside. Okay. For now, just try to remember the formula we previously used will be converted to this. Instead of just wi times xi, we will have wi times xi plus b. Okay. We will have all these inputs multiplied by the weights, and we will plus have b. Alright, and at the end we will use this z with our sigmoid function, and the output of this network will be this one. Okay, and this sigmoid function, this thing, is called the activation function. So this is one important concept. Please try to remember activation functions. There are some terminologies you are supposed to remember. That's one of them. So weight, input, bias, activation function. Up until now we have seen these guys, and you need to remember all this. So do we need to use sigmoid function as the activation function? No, you don't need to. There are basically a lot of activation functions. For example, there is Tanhash. We have sigmoid from the previous. We have ReLU that we will be seeing. So you can basically use any mathematical function. But there are some common functions that we will be using. You don't just use any function that you pull up. So this is another concept you need to remember, or another definition. A layer is the set of neurons that are all at the same depth with respect to the input. So when you are reading a neural network, you should start from the left. So this is the input layer, right? And all these guys are at the same depth. Although they don't seem to be at the same depth visually, you need to follow the direction of the input. So the input is going from this to this. That means this guy and this guy are supposed to be at the same level, although they visually don't appear at the same level. Okay, and these guys are supposed to be at the same level as well, and these yellow neurons are supposed to be at the same level as well as these guys. Okay, so we have basically this layer 1, 2, 3, 4, 5 layers here. So the black is always called the input layer. Usually you say this is the first layer, this is the second layer, this is the third, and this is the fourth layer. So please try to remember the concept of depth and layer as well. And other things to remember, this leftmost layer is called the input layer, the rightmost layer is called the output layer, and these guys are called the hidden layers. Okay. So building blocks of neural networks. So we have this concept of forward propagation. So what do we mean by that? We have a forward propagation as well as backward propagation. So that's why there's this distinction with. That's why we have this concept of forward propagation. Basically, things flow in this direction when you are doing forward propagation. So you have an input, you multiply your inputs with the weights, and then you add a bias here, and then you use your activation function, which we will be calling as G in this case, and you obtain the output of your network or your neuron. A network can consist of only one single neuron as well. Okay, and we have this activation function so that first we can have nonlinearity, and we would like to have real values. We don't just want zeros or one. We would like to make our decisions with respect to real values. So that's why we have the activation functions. Okay. So a little bit more advanced version of the previous network, which was this one, is this one. They are basically the same network, okay, with the forward propagation. But we have this special input, which is always 1, and we have this W0, which is the bias term, okay. So we called this B in previous slides. When you would like to have it more formally, you consider this as another input, which is always 1. This is constant. You cannot change this. You can change these inputs. Okay. The input of this network is 3 guys. You can just have 3 features to feed in. You cannot change this one. This is a constant input, and its weight, which is W0, is the bias term. And mathematically speaking, this was our activation function. The output is activation function the bias term plus the rest. Therefore, the I starts from 1. It doesn't start from 0. It's from 1 to m. We have m inputs, okay? We basically multiply the inputs with the weight. We get this term. And then we add the bias. And if we would like to write this in matrix form, as we usually do when we solve regression problems, then you can rewrite this equation like this, okay, where x is this one and w is this one. So w is basically the weights and x is basically the inputs, and this is still the bias, okay. We have this activation function which takes this matrix multiplication plus this one as the input, and when we use sigmoid function as the activation function, if you remember from logistic regression class, we had seen this sigmoid function. That's basically this one, okay, 1 over 1 plus e to the minus z. So what else we can use as the activation functions? We have the sigmoid function, our good old friend. And if you would like to use sigmoid function with TensorFlow, we basically have this expression. That's gonna we will be seeing this in detail, so don't worry. If you would like to use this expression, that's called the hyperbolic tangent, or usually we call this as tan h. Then we have this expression, and we have this strangely behaving function, which is called rectified linear unit. And if you would like to use this as your activation function, then that's called ReLU. That's a very popular one. All these three are very popular basically, but their usage is different. Okay, you usually use ReLU in hidden layers, but you use these two layers at the output, two activation functions at the output layers. That's one thing you need to remember as well. The activation function for every layer may change, but you need to be careful with the output layer activation functions. So why do we use these activation functions anyway? Why don't we just fire zeros and ones? That would be actually simpler. You could have just binary decisions. So if we had the 0 and 1 decision making neurons, our classification problem would look like something like this. Okay, this is just a binary classification. That's a linear separation of the space. But if you introduce activation functions, then we can introduce nonlinearity to our networks. So you can basically classify these two classes if you use neural networks, because we have nonlinearity in our networks. So please try to remember, activation functions introduce nonlinearity to neural networks. So instead of having something like this, once you use activation functions in your layers, you can get something like this. So this is the most basic form of a neuron. We have two inputs, okay, and one weight. And if you remember from our previous equations, what we were doing is we were creating a column-wise matrix from the weights, which is 3 and minus 2. We have the bias, that's 1. So our equation that's gonna fire basically the outputs becomes something like this. So it's 1 plus x1, x2, that's a column-wise matrix as well, transpose, since we're gonna multiply these two matrices, and that's the weight. And in the end, we come up something like this. And that's basically just a line, okay? And this is basically how we show this. So if we didn't have any activation function, what we were going to have was a line which was going to split the space into two in a linear fashion. Okay. But since now we have an activation function, instead of having a linear separation, we can get a much more complicated output. So, for example, let's take the points minus 2, 1, minus 1, 2, which is this one, okay? And if you put this point into the equation, for now, just neglect g, we have minus 6 here, okay? And since g will be the sigmoid function, we will have 0.002. Now you can use this online calculator if you would like to. You can, for example, enter minus 6 here. You can check whether that was correct. As you see, that's 0.002. That's the same result as we did. You can basically use this calculator in order to calculate ReLU as well as sigmoid and other functions. Okay. So there are two ways of representing the perceptron. We can use this equation, okay, or we can use this kind of equation. And there is this concept of dense layers and sparse layers. In this lecture, we will be focusing on the dense layers. The dense layer means everything is connected with everything. Okay. So this input is connected with all these two neurons. Okay, and this neuron is connected to all the neurons here, which means these are dense layers. Okay, if we had sparse layers, some of the connections were going to be missing. This is another definition or concept you should remember about the neural networks. So in TensorFlow, we will see how we can create layers. I will be skipping this slide because we will have two examples on TensorFlow. But if you're interested in, you can see how we can create a dense layer. When you say, for now, just forget about this. I will be explaining what this tf.keras means. And assume, just don't see this. We have these layers and we have this expression dense, which means we will be creating a dense layer. Okay. And this means this dense layer will have two neurons. Okay. When you see these units in TensorFlow, that means we will have basically this many neurons in this layer. And we need to create layers one by one if we are going to use sequential layers. But for now, just skip this part of the slide. Just focus here. That's how we create basically layers with TensorFlow. Okay. And how do we basically calculate something in this layer, for example? Let's say we have this many neurons in this layer, okay? And the output of, for example, Z3 is this one. Let's say for generalization, Zi, that's gonna be W0i, which is the bias of this neuron. And then it's gonna be the weights times the summation of weights times the inputs. Okay, that's basically this expression, this formula is giving for any of these Z neurons what's the output gonna be. Okay, and if you remember from the previous slides, we need an activation function as well. This is the bare output of this neuron. We need to use an activation function, so the final output basically is this one. Okay, so that's the same thing. Basically, these are multiplications and summations. There is nothing complicated actually. You just need to multiply the inputs with the weights, sum here, and then apply an activation function and then transfer this to another layer. Okay, this is basically how neural networks work. So how do we basically create these layers? So Tensorflow is basically the library we will be using, and Keras used to be another library. Now they are basically the same thing. So Keras is now inside Tensorflow. So if you are creating layers, you will be using Keras from Tensorflow. And the way we import is, as usual, import TensorFlow as TF. So the layers we will be creating are sequential layers. That's why I said you need to read the networks from left to right. So sequential, this is the first layer, this is the second layer, this is the output layer, okay? And if you wanna basically create, for example, this network, this is just the expression you need, okay? You first need a dense layer in the sequential network. This is going to be the first layer which has n neurons, okay? You have n neurons here. And this is the input layer, and this is the output layer. You don't need to define this one. And in order to define this one, you basically say we have another dense layer which consists of two neurons. Okay, and with these 3 lines of code, you created this network. So this is the network creation phase, and the other phase is network training phase. And we need more definitions and we need more concepts to train our network. So that's basically the same thing. We have the hidden layer, and the output of the hidden layer depends on the previous layer. So if you're basically at the kth level, so this means this is the first neuron of the kth level, okay, your output depends on the k minus 1th layer, which is the previous layer. Okay, you rely on the output of your previous layer. And this is basically how you define a more complicated network. Let's say you have a lot of layers. You add a dense layer, N1, N2, whatever, and at the end you add another dense layer which consists of two neurons. Okay, that's pretty simple. For each layer here, you add another dense layer. Okay. So let's see how we can basically apply neural networks. Assume that we will be solving the problem to see whether a student will be passing the class or not. And let's see what are our independent variables. That's the hours spent on the final project and the number of lectures you attend. So the probability you pass from the class basically increases if you attend more classes, which is this axis, x-axis, okay. If you attend a lot of classes, then you are here. And if you spend a lot of time on the final project, you are here as well. Okay. So basically our labeled data says if you are on this region, you pass the class, and if you are on this region, you fail the class. Okay. And we would like to solve this one, whether this guy will be passing the class or not. Okay. So what we will be doing is we basically have two input variables because we have this. Okay, we have x1 and x2, two independent variables. So in our network, we need to be able to feed two data. Okay, number of lectures attended and number of hours spent. These are two variables. So this is gonna be our input vector, that's gonna be our hidden layer, and this is going to be our basically the output layer. And since the network was not trained beforehand, assume that it predicts 0.1 for this right over here. Basically, if we see a point here, this student should pass, right? Because that's basically closer to the students that passed the class. But since our network was never trained, it predicted this value as a 0.1. Okay, that means we have some error. Okay, and assume L gives the error between the predicted value and the actual value, this function. So this is the actual value, which is 1 in this case, and this is the predicted value, which is 0.1 in this case. And assume we have data from multiple students, then we can basically calculate a total error or a summation of the errors, which is this one. Okay, let's say we have n students. Basically, we have predictions and the actual values for the students. We can basically calculate the summation of the losses or the errors. Okay, so that introduces another concept called a loss function. And a loss function is a function that compares the target and predicted output values, measures how well the neural network models the training data. When training, we aim to minimize this loss between the predicted and target outputs. So if your loss is 0, basically your prediction is perfect. Okay. In this case, for example, we have a prediction of 0.1 and the actual value is supposed to be 1. And there is a significant difference between the prediction and the actual value. And the aim of training a network is to find the weights and biases so that your output's loss is small enough. Okay, so we would like to minimize a loss function. So this is one thing you should remember. The aim of neural networks is to minimize a loss function. Okay. Okay, so let's see a little bit more about the loss function. So a loss function is a function that compares the target and the predicted output values, measures how well the neural network models the training data. When training, we aim to minimize this loss between the predicted and target outputs. That was the definition. Okay. So we have two types of losses because we usually have two types of problems. We have regression problems and we have classification problems. That was basically same with the machine learning. We started with regression and then we went through classification. If we have a regression problem, then we use these loss functions like mean square error, mean absolute error. Okay, this used to be the case with our regression problems as well, and it's the same with the neural networks. If you are trying to predict a real value with regression, then you need to use a loss function like mean square error or mean absolute error. But if you are trying to solve a classification problem, then we have other types of loss functions like binary cross entropy and categorical cross entropy. We will be seeing these guys in detail, so I'm not gonna go into the detail. But for now, just remember you need to minimize a loss function for the neural network. And you're not going to do this minimization by hand, don't worry. You don't need to know the mathematics behind this. It's quite complicated. We will be seeing a little bit. But when you define your network, you first create your layers, okay? And then you tell your network which loss function it's gonna use and which optimizer it's going to use to optimize that loss function, to minimize that loss function. But for now, just remember we have different types of loss functions and we need to minimize this loss function. Okay, so how do we train these neural networks actually? Okay, so gradient descent, our good old friends. You should remember this image from our previous classes. So we will be using gradient descent again for this problem. But in neural networks, the situation is a little bit more complicated. But let's start with a simple scenario. Assume that we have W0 and W1 that we would like to minimize or maximize. And let's say we have a loss function J, okay, and it's giving the result something like this. And the idea is we would like to find the minimum of this loss function for W0 and W1. Okay. So how can we train the network, which means determine the weights and the biases so that the loss is as small as possible? So that's the optimization problem. So remember what we were doing with the gradient descent? We randomly pick a point. Let's say we pick this point, W0, W1. Okay. And then we calculate the gradient at that point. And what gradient gives is, it's basically the direction to maximize that loss. But we want to minimize the loss. We don't want to maximize the loss, right? We just want the opposite of that. So we get the opposite direction of the gradient because we would like to minimize the function. We don't want to maximize the function. We don't want to climb the hill. We want to go down the hill. Okay. So we get the gradient and we get the opposite direction of the gradient afterwards. So that's how we calculate the gradient basically, and then we go in the opposite direction of the gradient, and we repeat the procedure. When we are here, we calculate the gradient, we take the opposite of the gradient, and then we go in that direction for couple of steps, and that couple of steps were called learning rate. If you remember from the previous lectures, the length of the steps we are taking was called the learning rate. Okay. So once we cannot move down anymore, that means we are at a minima. That doesn't necessarily mean it's basically the global minima. It may be a local minima as well. We could be able to end up here, or we could end up here as well. Therefore, we don't just rely on one point because that was a randomly picked point. We repeat this procedure until it is converging to something. Okay, and this procedure was called gradient descent. That's the technology. That's the idea behind minimizing the loss optimization, and we had covered this gradient descent basically in our previous lectures. So how do we do it? Basically, you're not gonna use this kind of algorithm. You will always tell your network to do the optimization by itself. But just for the sake of mathematics, let's try to understand what the algorithm is doing. Basically, we initialize the weights randomly. That's like picking this point randomly. Okay, so this is this step. Initialize weights randomly. And if you wanna write this code in TensorFlow, that's basically this. You initialize the weights randomly. Okay, and then you loop until convergence. And in the loop, you always compute the gradient. Okay, you compute the gradient, you take the opposite direction of the gradient, and you update the weights with the learning rate. So it's here. You update the weights, that's weight minus learning rate times the gradient. Okay, and that's the new weight. And you repeat this procedure until the convergence. So this LR is the learning rate. Gradient is basically the gradient of the loss, the current loss. Okay, But as I said, you will never ever be implementing this function. Just for the sake of mathematics, try to understand what's the idea behind gradient descent. You will never ever be implementing this. So in neural networks, we were trying to optimize basically the weights and the biases, right? And in a normal neural network, you have like millions of these weights and biases. It's not like a couple of thousands. You have millions of these weights, and it's basically not that easy to use stochastic gradient descent or gradient descent. That's why we need to use something called backpropagation. And the way it works is basically if you are interested in, for example, the weight in W2, if you want to calculate this one, okay, you basically get from here. You take the derivative of this one with respect to y. This is the chain rule, if you remember from calculus. And you take the derivative of this one, okay? This is equal to this one. So if you want to calculate this, you take the derivative from this direction. That's why it's called backpropagation. In forward propagation, we were feeding input from this direction, from left to right. If you want to calculate the gradients, then we come from right to left. That's why it's called backpropagation. Similarly, if you would like to calculate, for example, W1, you need to take the derivative of this one with respect to W1, right? And in order to calculate the derivative of this with respect to W1, you apply chain rule again. You get the derivative of JW with respect to Y, Y with respect to Z1, Z1 with respect to W. Okay, that's what's called backpropagation. So, what does it look like if you visualize a loss function? It looks like something like this. So it has a lot of peaks, it has a lot of valleys. So it's highly likely that you can get stuck on a local minima. You see, these are all local minimas. And since we have quite a few variables to optimize, you usually come up with something like this. And depending on your learning rate, the step you take in each iteration changes. Okay, so if you have too small learning rates, then you may get stuck, or it may take too much time to find the minima. So we would like to come to here. Okay, this is the minima, global minima, but we don't want to get stuck at here, right? So we need to use a learning rate that can jump over this, or that can jump over these guys, and it can come to here. But if we use a too big learning rate, we may overshoot and miss the optimal. Let's say we are here, okay, and somehow we are going in this direction, and our learning rate is too high, so we came here, and then we jumped over here. We jumped over the global minima. So if you use a too big learning rate, the training phase doesn't take too much time. The training is easier and it takes less time, but it's quite likely that with a too big learning rate, you may miss the global minima. So that's one thing you should remember as well. If you use a too small learning rate, you can either get stuck at a local minima or it may take too much time. If you use a too big learning rate, you may overshoot and miss the optimum point. Okay, so are we going to implement all these things, or are we going to use a library? So for the sake of simplicity and for the sake of your brain power, you will not implement any of this. You will be using TensorFlow. You will only tell TensorFlow which optimizer you would like to use. So these are the optimizers: stochastic gradient descent, Adam optimizer, Ada delta. All these things are optimizers, and you need to define a loss function. That's it. Before the training phase, when we are creating our network, we first create our layers by defining the number of neurons each layer will have and the activation function this layer will be having, and then we need to define which optimization algorithm the network will be using and which loss function it's going to optimize. Okay, those are the important steps for the neural networks. So let's try to put it all together. That's basically we define an optimizer and then we basically try to define the network. Okay, and you will see in the examples that that's easier. I mean, you don't need to deal with all these things anymore. You don't need to define your gradient descent function. We will be using the optimizer. And computing the gradient descent for every sample is very time consuming. Therefore, we can use stochastic gradient descent. That's basically more or less same with the gradient descent. As I said, you don't need to care about this. We will be using the library. Just try to remember the idea behind gradient descent and the stochastic gradient descent. You pick a random point and then you go in the opposite direction of the gradient. Okay. So there is another concept called regularization. For a couple of weeks, we will not be using this terminology, regularization, but just remember, in order to avoid too complex models that may lead to overfitting, we can use regularization for more generalized models. That basically means during the training, we randomly set some activations to 0, which basically means we drop some of the layers, okay, some of the neurons in layers. For example, this is a very complicated network. We don't want something like this. This is too complicated. That takes too much time. And if you have a network that looks like this, it's highly likely that it's gonna memorize. Okay, you don't want your network to memorize so that it can generalize. That was the same problem in our previous lectures when we work on regression and classification. We don't want our model to overfit. We don't want our model to memorize stuff. Okay, we want our model to be able to generalize. Therefore, for the sake of generalization, we drop some neurons from each layer. Usually we drop 50% of the layers so that our network doesn't memorize anything. And this is done by using the dropouts. Okay, that says just drop 50% of the layers, 50% of the neurons in each layer. So when we are training our neural network, we need to be careful. Neural networks can overfit as well. Even if you apply dropouts, and even if you take care of some stuff, they have a tendency to overfit as well. If you have too many iterations, for example, training iterations or what we were calling as epochs. If you have too many epochs, then it's highly likely that you will overfit. Okay, and you can basically see whether your network overfits or not by following the loss function. So if your loss function decreases gradually for your training data, but for your testing data, if it decreases and comes to a plateau, and then somehow either it goes stable or it increases, that means you need to stop here. That's the point where your neural network is trying to memorize. Okay, you need to stop where you need to know where to stop, and this is really the point you should stop for this network. For example, if you keep going, that's gonna memorize. It's gonna memorize more, and you will lose generalization. on this side of the graph. Okay, so you need to know where to stop. Okay, so we have seen the concept of perceptron, that you said these are the structural building blocks, and they could just basically output zeros and ones, or we can use activation functions so that things are non-linear. We can stack neurons, we can stack perceptrons to create neural networks, and we can solve optimization problems with the backpropagation. So the idea was to find the weights and biases of all these neurons. And then what we have seen is there is a phase called neural network creation, which is this phase. You basically define your network, and then you basically train your network. And during the training phase, we tell the neural network which optimizer it's gonna use and which function it's basically going to optimize. Okay. So for the rest of our lecture, we will be using Google Colab. We will not be using our computers because most of us do not have GPUs on our computers. You need to have GPU. Basically, the TensorFlow works on CPU as well. You can give it a try. It works a little bit slower, but if you have a GPU, you can definitely give it a try. If you are under Windows, it's a little bit tricky to install all these libraries. Therefore, I strongly suggest you to use Google Colab. I will be showing how we can basically use it. It's a cloud service from Google. You can run your deep learning code. You can basically run your machine learning code in Google Colab. It's like our Jupyter notebook that we used so far. There are slight differences, but the good thing is you don't need to care about which TensorFlow you are using or whether you did the installation correctly or not. So I strongly suggest you use Google Colab. In order to use Google Colab, there are a couple of things we need to do. First of all, you need to have a Gmail account, definitely. And then you need to use your Drive, Google Drive. So this is my Drive, for example. These are my files in Google Drive. And in order to use Google Colab, that's a different service. At the first entrance, it's gonna ask you some credentials. Once you are done with that, it's not gonna ask you anything anymore. As you see, this is basically quite similar to the Jupyter notebook. We have our cells, we can execute Python code. The only difference is we need to have our drive mounted to Google Colab so that we can make use of data. Okay, and in order to connect to the Google Drive, you need to execute these two commands. Okay. Now it's mounting Google Drive. That may take a little bit time, depending on how busy the servers at Google. So this is done. We will mount this. We will connect to Google Drive. That's gonna ask you some credentials. You need to allow that. You see, now we have this. Okay, you may have some notification from Google. You may need to basically allow for entrance from Google. You may need to say it was me who was connecting to my drive. But once you are connected with your drive, you can see the content of your drive. It's usually mounted as my drive. That may change depending on the version you are using from Google, but for example, my data, my CSV files are located here. We will be using, for example, for the first example, Celsius to Fahrenheit CSV, and then we will be using the bike sharing daily CSV. So right now, from Google servers, I can use my CSV files that I uploaded to Google Drive. Okay. And in order to upload to Google Drive, you can just drag and drop to wherever you want. So let me show you my wherever I put. So that's where I put the content of our lecture. So we will be, for example, using the Celsius to Fahrenheit CSV in the incoming lecture. So that's basically how we will be using Google Colab. That's basically quite similar to Jupyter Notebook. So if you are familiar with Jupyter Notebook, you will have no problem using Google Colab. It's actually simpler. You can either add code or text. You can press this button to run the cell. It's the same logic with Jupyter Notebook. You have cells. You need to execute this cell so that if this cell depends on this cell, you first need to execute this cell. So it's the same logic with the Jupyter Notebook. Okay. So for the practical example, we will be converting Celsius to Fahrenheit. That's a very simple problem. If you remember from high school physics, that's a very linear problem. So we have Fahrenheit versus Celsius, okay, as in this graph. And there is a linear relationship between Celsius and Fahrenheit. And it's basically this. It's the Celsius times this number plus this number. Okay, this is a very concrete formula. By just applying this formula, you can basically convert Celsius to Fahrenheit. No problem. Okay. And as you see, this is basically the equation of a line. Okay, y is equal to x times a plus b, right? Y is equal to x times a plus b. And we would like to predict a and b since we don't know these guys. Okay, and the neural network we will be creating will have input as Celsius, and it's gonna convert this Celsius into Fahrenheit. And during the training phase, we will feed this network with a lot of Celsius and Fahrenheit degrees, and then our network will learn the weights so that it can make a prediction about converting the Celsius into Fahrenheit. Okay, that's the thing we will be doing. So let's go back to Google Colab for that. So this is new. This is import TensorFlow STF. Usually you import stuff as TF. That's the abbreviation for TensorFlow. So I strongly suggest you use this convention, TensorFlow as TF. Okay. So it's gonna import the TensorFlow that's already installed in Google Cloud. Okay. And in order to see the version of TensorFlow, you just say print TensorFlow version. It's 2.12. That's a brand new version of TensorFlow. So that's the good thing about using Google Colab. You don't need to basically deal with installing TensorFlow or other stuff. It's already installed for you. You can basically use the pre-installed stuff. You can install it for yourself as well, but you need to reinstall everything from scratch if you close Google Colabs. But if you install stuff that's already installed, then you can continue using it. So right now, Google have 2.12 as a TensorFlow version. You can just import it and start using it. The bad thing about Google Colab is since they may change versions. For example, when they change Seaborn version, sometimes there are subtle differences. For example, for plotting stuff. So your code that was executing previously may not execute. So that's the negative side of Google Colab. Since the version control is not on your hands, if Google changes something, then you may need to revise your code and correct some stuff. So that's the downside of using Google Colab. But it's for free. It's quite powerful. It can use both GPUs and TPUs. And for your small projects, you can just use it, start implementing stuff, and then get some results. Okay. So this is, as usual, we imported NumPy, Matplotlib, so that we can plot stuff. So you can plot stuff with Google Colab as well. So it's basically like Jupyter Notebook. We already did this. We mounted the Google Drive, so I'm not going to execute these two cells. So this is where we read our CSV file. Now remember, we mounted the Google Drive, and our CSV files are located inside My Drive TensorFlow, and this is the CSV file we will be using. This part may change. Please do not get confused, but the idea is try to find your CSV file in your Google hard drive and try to read it from there. Okay, but it needs to start with content drive. This My Drive may be different for you, and after content you can just write this drive that's coming from here. My Drive is coming from here. This My Drive is coming from here. That's TensorFlow 2. That's a directory I created. So you can create your directories in Google Drive like this one. And the CSV file, that's something I loaded previously to Google Drive. So that's it. We created our data frame with pandas by reading Celsius to Fahrenheit CSV. Now let's see what we have inside our CSV file. So we have basically Celsius and Fahrenheit degrees. For minus 50 Celsius, we have minus 58 Fahrenheit, and that's going on like this. Okay. If we plot this data frame, what we will be seeing is this is a linear relationship. Okay, that's quite linear. This is as linear as it can get. Okay. So as we usually do, we will be creating our X train and Y train variables. We will be feeding Celsius for training, and after predicting the Celsius values, we will be using the Fahrenheit values to train our network. Okay, this is where we fill our X train and Y train. Let's take a look at the shape of X train. There are not so many data points. We have 30 data points in our data set. You don't need to have a lot of points because that's gonna be like the simplest neural network ever. We will have just one neuron with one input. Okay, this is like the simplest form of neural network. You can't have anything simpler than this. Okay, now comes the funny part. Now we will start creating our network, defining our network. So it's gonna be a sequential network. Even if we have one neuron, which is this one in this case, we will have just one neuron. You need to define what type of network that should be, and it's gonna be a sequential network. And once we define our model, we said the model is gonna be a sequential model. It's gonna be a Keras model, Keras sequential model. Then we start adding the layers. Okay, and the way we add layers to our network is we use add command, and we define the type of the layer we will be adding. It's going to be a dense layer with one neuron. Okay, this is, if you remember from the previous lecture, this says in my dense layer that I'm adding to my model, I will have one neuron and I will have one input to that neuron. Okay. This is really the simplest ever network you can see. So let's execute this so that we can create our model. So this is an important command, model.summary. Once you create your model here, you add your layers here. This command is giving you the shape of your network. Okay. And it says basically, your model is a sequential model. Okay. And you have these layers. If we had more than one layer, we were going to have a couple of rows here as well. But since we have just one layer, which is a dense layer, that dense layer has two parameters. So just think about it. Why do we have two parameters basically? The first parameter is the weight, because we have one neuron, which means we need to have at least one weight. We have one input here. So it has one weight and one bias. So we need to optimize two parameters. As I said, this is like the simplest ever network you can create. You have just two parameters, one weight and one bias. Okay. Now we defined our model, okay, the sequential model, and we added a dense layer with one neuron, one input. Okay. Now we need to tell our model or our network which loss function it's going to use. Since this is a regression problem, we need to use this kind of, for example, mean squared error. Okay. If you remember from the previous lecture, we need to define a loss function, and for regression and classification problems, we had different loss functions. And since this is a loss regression problem, we will be using mean square error as loss. And we need to tell TensorFlow which optimizer we will be using. Okay, in this case, we will be using Adam optimizer. And the command we basically introduced this optimizer, and the loss is model.compile. Okay. And once you execute this, that doesn't take any time because it's just telling the model we will be using the Adam optimizer as the optimizer, and we will be using mean squared error as the loss function. Okay. So these are all definitions. Nothing fancy is going on here. This is creating a sequential model. This is adding a dense layer with the number of input neurons you define here. And this is basically defining the optimizer as well as the loss function. Nothing fancy for now. Okay. And this was basically the definition phase of our neural network. Now we will be training our neural network. And as we always do, we will be using the command fit. We will feed the fit with X train and Y train, and then we will be defining the number of epochs we will be training our network. So we will have 100 epochs to train our model. Let's execute this and discuss what we will be having. So that's a quite long list. Okay, this is the first epoch. As you see, we have a quite big loss here, and in each step the loss is decreasing and decreasing, as you see, and at some point that's becoming pretty small. So it's fluctuating around 1 and 5. Then it's becoming better. Then it's coming to a plateau as well. So at the 100th epoch, we have a loss like this. Okay, that's kind of fine from my point of view. But this is a very, very simple network, so you don't need to train this a lot. And if you remember from the previous lecture, we need to plot this loss so that we can see what happened during the training phase. In order to plot the loss, the command we will be using is, first we need to get the epoch history. And we get the epoch history from history.keys. Okay, that's gonna give us a dictionary. And then we will be using matplotlib to basically plot the history of the loss. So this is what happened. Basically, we started with a pretty big loss that decreased, that somehow increased, then decreased again. There are fluctuations, but as you see, the trend is always going down. And then we come to a plateau here. Actually, we could just use 40 epochs. We didn't need to use all these 100 epochs, but for the sake of example, we just made the epoch number as 100. You see, it's always a good idea to cut somewhere here so that your network doesn't memorize, but there is not really so much to memorize since we have two variables here. I mean, we have just one weight and one bias, so we cannot really memorize a lot. Okay. Let's see the weights. That gives us the weights, and since we don't have so many weights, we have two weights. That's a floating point, which is 1.8. That's basically the 8. Okay, if you remember the Celsius to Fahrenheit formula, let me show it again. It's this one. That was A, that was B. And as you see, that's almost 32. It's not exactly 32, that's close to 32. These are not exact numbers. I mean, this is kind of an exact equation for converting Celsius to Fahrenheit. But what our one neuron neural network learned is, it's quite close to 9 over 5 and it's quite close to 32. Okay, so our model was actually quite successful. Our one neuron ultra simple, super simple model was able to predict or learn these weights. And let's try to convert 0 degrees to Fahrenheit. That's close to 32 Fahrenheit. As the formula suggests, it's supposed to be 32 Fahrenheit degrees. So you can basically check it from the weights. So the weights are correct, therefore that's a linear formula. Our model worked, and it could be able to predict the parameters to convert Celsius to Fahrenheit. That was a one neuron, ultra simple, super simple neural network that we could be able to create with Google Colab and Tensorflow. So this is basically the neural network we created. That's, as I said, the simplest ever neural network. It has one bias, one input, one weight, one output. And the output is basically input times the weight plus the bias. It can't get any simpler than this. So in our second example, we will be calculating the bike rental usage. And the objective is to predict the bike rental usage based on inputs such as temperature, humidity, wind speed, and other stuff. Okay. And this problem is much more advanced compared to the previous example, because we had one neuron, we had one input. Now we have quite a few inputs. So we need to use or build a multi-layer perceptron network. So the network we will be creating will be a little bit more complicated than the previous example. So what are our inputs? So it's instant record date, record index, the season, it's either spring, summer, fall, winter. It's the year, month, or it says whether it was a holiday day or a working day. There is some information about the weather situation. These are categorical data. There is temperature in Celsius. There is wind speed. Okay, and the output is a class casual register and count. And that's basically the count of casual users, that's basically the count of registered users, and this is the summation of registered and casual users. So we have these guys as independent variables, and we have the output as the number of bytes being granted depending on these variables. That's the problem we will be solving. So that's a regression problem, if you remember from our previous lectures. And we will be solving this regression problem by using neural networks. So these are the inputs we will be feeding to our more complicated neural network. And then we will be getting the byte usage counts depending on the input. Okay. So that was basically the neural network we created for our Celsius to Fahrenheit ultra complicated neural network problem. So the neuron collects signals from the input channels. Just to summarize the stuff. So these are dendrites. This is where we basically put the input. This is the neuron itself. This is the output. Just for the summarization. So you should remember all this stuff. That's the bias. These are the weights. This is the input. This is how we basically evaluate these guys. And we have either step functions or other activation functions. We covered all this stuff. So we can have a sigmoid function here as well. So for more complex networks, while we define the layer, we need to define the activation functions as well. And for the sigmoid function, it takes a number and sets it between 0 and 1. Okay. So it's basically mapping the space between 0 and 1. So it converts large negative numbers to 0 and large positive numbers to 1, as you see, because of its S shape. And the sigmoid function is usually used in the output layer. That's something you should remember. So for activation of output layers, we either use sigmoid or we use hyperbolic tangent. So ReLU is a little bit different than sigmoid function. You see, if input is smaller than 0, the output is 0. And if the input is higher than 0, then the output is basically the input. So it's basically mapping negative values to 0 and preserving all the positive values. That's rectified linear unit function. And we use this activation function for the hidden layers. That's generally is being used for hidden layers. So sigmoid was mapping between 0 and 1. That was an S shape. This is a weird shape which basically maps all negative values to 0 and preserves all the positive values. And hyperbolic tangent is actually quite similar to sigmoid function, but it converts numbers between -1 and 1. In sigmoid case, it was mapping numbers from 0 to 1. And unlike sigmoid, hyperbolic tangent outputs a zero-centered range. Okay, that's the basic difference. And in practice, people have the tendency to use hyperbolic tangent over sigmoid. Okay, because the mapping is much better. But you can use both sigmoid and hyperbolic tangent. Don't worry about that too much. But for the outputs, try to prefer hyperbolic tangent on sigmoid. Okay, so this is again the stuff we covered, so I'm not gonna go into the details of this. This is basically how we represent this complicated network. Let's dive into the example. I think that would be much better. Let's go back to the Google Colab. The way I usually use Colab is actually I go to the drive, my Colab notebooks. That's another directory, and then I click on this. The thing is, when you open it initially, that tries to map uh, the drive, so it's mounting the Google Drive. That may take a little bit time, but in order to read our bike sharing daily CSV file, we need to mount that, and you can execute this. That's not gonna help a lot, but it takes a little bit time to mount the drive. While it's mounting, we can basically go back to our previous example to see what we have covered for creation and training of the network. So we had this definition. We said we will have a sequential model, and then we will basically have this layer, this dense layer that consists of one neuron, and this one neuron takes one input. Okay, that's basically what we did for the previous example. And the other thing, while we were defining the model, was we defined the optimizer as well as the loss function, and then we fit the model. We will be following the similar strategy with this one as well, but we're still waiting for Google to mount the drive. Still didn't mount the drive. Okay, now the drive is ready. So we will be importing TensorFlow, NumPy, Pandas, Seaborn, the usual stuff. Importing TensorFlow may take a little bit time. Don't worry. Now it's ready. We don't need to execute the cell. Now we will be reading this bike sharing daily CSV with Pandas. Now we created our data frame. And when you take a look at the data frame, you see we have the sequential number, we have some dates, we have the season, we have year, month. It says whether that's a holiday or not, that's a weekday or not, whether that's a working day, weather situation, temperature, humidity, wind speed, and we have these numbers, which is basically the registered casual users, registered users and casual users, and the summation of these two. Okay, this last column is basically the summation of these two. Therefore, we can basically drop these two layers, the casual and registered. We have this information covered in the last column. We can see whether there is any null inside the data. I already did that. There is nothing to drop because there is no null. So we can drop instance, since this is just an index. As you see, that's a sequential number. That's 1, 2, 3, 4, 5. That doesn't help for anything. That's just sequential number. So we don't need that. We just drop it. Okay. And once we drop it, we come up with these guys: the date, season, year, month, and other stuff. Okay. And as I said, this count is the summation of casual and registered. This is still data preparation. Okay, this has nothing to do with creating the neural network. We are preparing the data so we can use it. So we will be dropping casual and registered. By executing this line, we dropped basically the casual and registered. And after that, if you take a look at the data, we just have these columns. Okay. And in order to make use of dates, we will be converting it to a numerical value. That's something new. We haven't done this so far. Once you do this, you have something like this. Okay. And when you execute this date time index, that's a special command for pandas, we come up with something like this. Okay, we started using the date as the index, and since the index is the date, we don't need this column anymore. Okay, we can drop this. We don't need this. Now we have something like this. You see, we have the date as the index, and we have the rest of the columns. Now the pandas has another interesting command called sFrequency. By using this W, we can plot the weekly bike rental usages. Okay. And we can do this because we converted this date into the index by using this command and this command. Now we have date as the index. We can plot the data with respect to weeks. Okay. And we can see the frequency of bike usages with respect to weeks. I'm not going to execute this command. That takes a lot of time, pair plot, because we have a lot of independent variables. You can execute this yourself to see what's going to happen. Now we need to get our numerical as well as the categorical data, because we have temperature, humidity, and wind speed, as well as the count of usage as numerical values, and the rest is categorical values. So let's get these guys as X numerical. So we can see whether there is anything correlated. We don't need to do that. The neural network doesn't care about this. So we need to get the categorical data as well. The season, year, month, holiday, weekday working, and weather situation. These are categorical data. And if you remember from our previous exercises, we use scikit-learn one-hot encoder in order to convert this categorical data into numerical data. Okay, and this is what it's gonna do. Okay, and when you take a look at X categorical, you will see a lot of columns. And if you take a look at the shape, we have 32 columns. We converted this 1, 2, 3, 4, 5, 6, 7 columns into 32 columns because we use one hot encoder and we converted all this categorical data into numerical data. Okay. Now we can concatenate. First, we need to convert this into a pandas data frame. Okay. Now, when we take a look at what we have in numerical, we have these guys. Then we concatenate the categorical as well as the numerical data to come up with all the columns of our data. When you take a look at the shape of the data, we have 37 columns. Okay. We don't need this column because this is just an index. So we drop this. Okay. And then we will use the rest of the columns apart from count as the X value and count as the Y value. Okay. And when you take a look at X shape, we have 35 columns as independent variables with our categorical data converted into numerical data, and we have Y shape as 1. So this is basically number of rentals, and these are our independent variables. Now we need to scale our data because humidity, temperature, these are all from different spaces. If we just use them as they are, we're not gonna get anything. So we will be using min-max scaler from scikit-learn pre-processing, and then we will be scaling our data. We will be using train and test split to get 20% of our data for test and 80% of our data for training. Okay, here comes the interesting part. So this is basically the definition of our network. So as the previous example, we define our model as a sequential model. Okay, that's the same. Then we add a dense layer which have 100 neurons and it has an activation of ReLU and the input shape is 35 since we have 35 columns in X. You only define this input shape for the first layer. Okay, that's something important you should remember. You don't need to define this for the rest. It automatically calculates, but for the first layer you need to define the input shape, and in this case it's 35 because we have 35 columns. Okay, so this is the first layer and this is the second layer. It's quite similar. It's a dense layer with 100 neurons with an activation function of ReLU. We have the third layer similar to the second layer, and we have another layer which is the output layer with one neuron and activation function linear. Okay, so that's gonna make a regression. So we will just have one neuron because we just one number. We just want to have one number as a result. Okay, we don't need a lot of neurons to fire stuff. We just want a number. We will give 35 inputs. We would like to have the predicted bike rental usage. Okay, so let's execute this. This was the definitions. So let's take a look at the summary. You see, for each layer we have the number of parameters. We have the shape that says we have 100 neurons for the first layer, we have 100 neurons for the second layer, 100 neurons for the third layer, and 1 neuron for the last layer. And these are the number of parameters we need to optimize for each layer. And in the end, even for this very small network, which consists of 4 layers, we need to optimize 23,000 parameters. Okay, these are all weights and biases. And we need to define the optimizer. The optimizer will be an atom optimizer, and we need to define the loss function. It's gonna be mean squared error. So by doing that, we are done with model definition. And this is the training phase. We will have 20 epochs for the sake of simplicity. Now we have something called batch size. I'm not gonna go into the details of this. We will be discussing this in the next lecture. But for now, assume that you don't use all the data. You just use some of the data for each epoch. Okay. Let's execute this. That may take a little bit more time than the previous example, but since we had just 20 epochs, it's completed. And we will be basically plotting the loss here. And as you see, the loss started big and started to drop. That looks like it came to a plateau. That doesn't mean that actually converged. We just applied it for 20 iterations or 20 epochs. We could have applied it even more. And if you take a look at the tests, X and Y values, so we predicted Y values for our text, and then we plot the results. You see, these are the predicted values on x-axis. These are the real values. As you see, they're quite okay. If it was perfect, that was going to be a line. But as you see, that's slightly scattered over a line, which means our model worked quite okay. So there are more formal ways actually to make better predictions about the performance of of our neural network, but for our very simple second neural network, we can see from this graph that it performed pretty well. So that was basically end of the practical parts. Let's summary content of this week. We have seen why we need to use deep learning, because if we can feed the neural network with more data, we can improve the performance, which is not the case for classical machine learning algorithms. So deep learning is good. And we have seen the definition of neuron. And in biology, we saw that there is this concept soma, dendrites, and axon. And the mathematical definition for this biological neuron is this one. And this part is the soma. These are the dendrites. We have inputs, we have weights, we have a bias, and we have an activation function. And we have seen this activation function is used to introduce nonlinearities to the problem. And then we have seen we need not one neuron, but we need a lot of neurons and a lot of layers in order to solve complex problems. In order to define our neural network, we need to define the layers. We need to define the activation functions of these layers. We need to define the loss function, as well as we need to define the optimization that we can use for that neural network. So that was it for the neural network introduction, the basic definitions and initial creation of the networks.